Hi, today we're going to figure out how to differentiate a function of a function. A function is just something that takes a variable as an input and outputs another variable. So a function of a function is a case where you have one function taking a variable as an input, then another function takes the output of that function as input to find the output of the variable. So let's say for an example we want to differentiate x squared. How do we go about doing that? Well, consider the general functions g of x and a function of that function fg of x. Ideally, we'd like to figure out a way to split the differential of a function into differentiating each of the individual functions, simplifying the matter. So let's take the differential of g of x with respect to x and see what we get. Here's our definition of differentiation. Let's just rearrange it so we get a term that tends to 0 as h tends to 0, and let's call this term a. So as h tends to 0, a tends to 0. Let's now rearrange to get just g of x plus h, so later we can figure out what fg of x plus h is. This is an important part of the formula to figure out the total derivative. Multiply by h to get this, then using the distributive property, bring the h out to the front. Now add g of x, so we now have g of x plus h as we wanted. Now let's take the differential of fg of x, but not with respect to x, but with respect to g of x. Since the differential with respect to g of x of fg of x is a differential of just the function f. Imagine replacing g of x with x, and you get the differential of fx with respect to x. So now in our definition of differentiation, rather than replacing x with x plus h, replace g of x with g of x plus h, since g of x is took the place of x. However, since we used h before for the change in g of x, let's relabel this one k rather than h as usual. Now I can follow the exact same method as shown above, but changing g of x to fg of x. I'll leave this as an exercise to the reader if you wish to do it, however you should be able to tell they'll just be the same since we're just relabeling some variables. Doing that we get the quantity b, analogous to a, with the variable changes. We also arrive at this quantity, the same as line 9 with the variable changed. The line shown here are the arrows. Now if we use the quantity in line 9, we can then put both sides of the equation into function f to get this. Now if you look at line 13, shown with the arrows in comparison to the line we just arrived at, you might notice a similarity. The left hand of line 13, fg of x plus k, is similar to the right hand of our current line. If we just use k is equal to h multiplied by a, plus the differential of g of x with respect to x, we find that they are the same. We can choose k to be anything we like, it's just a variable. However, as these are the variables you would change in the definition of differentiation, they're particularly useful when they tend to 0, since that's the case when the right hand side of line 1, for instance, equals the derivative. But we can see now that they both tend to 0 together, as k is a term multiplied by h, and a term multiplied by 0 is 0. So as h tends to 0, k tends to 0. So now we've got that fg of x plus k is equal to the right hand side of the previous equation, fg of x plus h, when k is equal to this. So let's substitute in our value of k into line 13, shown by the arrows, and we arrive at this, just replacing k with what we've set it to now. Now let's substitute in what fg of x plus k is equal to when it's equal to fg of x plus h, and we arrive at this, after taking away an addition fg of x. We can cancel off the fg of x on the right hand side, and now divide by h. You can now see the left hand side is a definition of differentiation for fg of x when h tends to 0. We can cancel off the h divided by h on the right hand side. Now let's take the limit h tends to 0. Well, as shown in line 4, as h tends to 0, a tends to 0, so we can get rid of the a on the right hand side. As shown on line 16, as h tends to 0, k tends to 0, and k tends to 0 causes b to tend to 0 as well, just for the same reason h causes a to tend to 0. So we can get rid of the b, and we arrive at this. So we can now see that to differentiate a function of a function, you can differentiate each function and multiply them together. Let's take the example of x squared squared. Well, g of x in this case equals x squared, then fg of x equals g of x squared. So the chain rule is here. Let's substitute in, replacing g of x on the top of x squared, and fg of x with g of x squared. Well, we showed in episode 1 that the derivative of x squared with respect to x was 2x, so we can now put that in. Now we just need to differentiate g of x squared with respect to g of x. Well, that's just x squared differentiated with respect to x, but with x replaced by g of x. So that's just 2 g of x. 2 times 2 is 4. Now I substitute in what g of x is, x squared. Now x times x squared is x to the 3, and we're done.